So let's begin. Let me give you a very quick review. So it's been a while. So a review of what we've done so far in pairs of random variable, right? So we started a new chapter last week, and we started talking about how do you characterize more than one random variable. In particular, how do you characterize two random variables? And we said that the way to characterize them is through joint distributions, right? So one of the things we learned was something called a joint CDF, or a joint cumulative distribution function, and that is defined as the probability, as you can see, the probability that the joint probability of the event that the random variable capital X is less than or equal to small x, and the random variable capital Y is also less than or equal to small y, right? So so the joint CDF of two random variables, capital X and capital Y, is actually a two-dimensional function evaluated at small x and small y, right? And is defined as a probability that the random variable capital X is less than or equal to small x, and the random variable capital Y is less than or equal to small y, right? So this is the definition of joint CDF, right? Then we talked about some properties. Let me just skip over those and not discuss them here. Then we talked about something called the joint PDF, and joint PDF is nothing but the partial derivative of the joint CDF with respect to X and with respect to Y. Okay, and therefore, and as a result, the joint CDF is nothing but the double integral of the joint PDF, right? So that's a relationship that we should perhaps remember. Okay, and it's basically an extension of the things that we've done already, in the sense that we've done this already for a single random variable. Now we're doing it again, generalizing it for more than one random variable and for two random variables. And actually, we're going to generalize this even further for more than two random variables in the next chapter. Okay, and then following this, so one of the important things we did was marginalization, right? So in order for you to get a marginal PDF of X from the joint PDF, all you do is marginalize over Y, right? So this is what you do, right? This is what you do, right? So you take the joint PDF and you integrate, or you marginalize over the Y variable to get a PDF on X, and you marginalize over the X variable to get a PDF on Y. So you marginalize on the X variable to get the PDF on Y. Okay? This is important, and this is equivalent to, in some sense, the total of probability that we've done already. And then finally, the last property we did was that the probability that the random variable capital X and capital Y belong to a certain region A, as a certain two-dimensional region, is equal to what? You just integrate the joint PDF over that region A. Okay? You just integrate over only those values of X and Y that reside in that region A. Okay? So these are just a summary of some of the properties we did. One of the things I would like to mention here is that all of these properties are also applicable to PMFs, the probability mass functions. Okay, so you're welcome to look at the textbook. I will not discuss them in detail here, but the ideas is exactly similar. So where you, for PMF, you would replace the integral with a summation, right? And you marginalize over one variable to get the other instead, except that the marginalization is actually summation and not an integral, right? So the ideas are pretty straightforward. Similarly, if for a discrete set of random variables, if I say, okay, what is the probability that those discrete random variables lie in a certain region, you sum over that region instead of integrating over that region, right? So the ideas are very similar, and perhaps worth not our time at this stage. Okay. We did some examples. I am not going to go over the examples, just one correction that I think some of the students pointed out as well. I've corrected them in the notes. I make a specific note in the video as well, that correction, and that correction is basically a depiction of what this looked. Okay, so those of you who said something like this, thank you for that correction. So the PDF is really a semicircle, if you will, okay, and not that exponential thing that I actually did in the class. Okay, any questions that you have here about these topics that we've covered? And essentially, all of these examples are essentially calculus, right? So the reason why you went through them is just to give a very quick review of some of those multivariable calculus concepts in case you were rusty. Okay. G. Mohsen.
So we're discussing joint random variables, right?
Yes.
So let's consider two random variables x and y. So could there be any relationship between x and y, like x divided by y or x plus y? And all of these relationships would be valid, or would they be subject to change?
Okay. So you're saying, Kitty, when you say a relationship between x and y, are you saying there is a functional relationship between the two? Is that what you're saying?
Yes, sir.
How to tell आप देखें. So let's say I say कि there's a random variable which is uh, the mass of a certain body. ठीक है? And I say कि I am only considering those bodies which have a fixed volume. ठीक है? And the density is defined as what? Density is defined as the mass divided by the volume. Okay? So the mass is random. Do you think the density is going to be random as well?
Yes, sir.
Of course, it's going to be random. Okay? But it is one of the variables is actually a function of the other.
Right.
And this is a one-to-one function. Okay? So these are two random variables that I agree with you. So there's a random variable which is the mass. There's a random variable which is the density. And both of them are random variables in their own right. Right? But there is a statistical relationship between the two. And what is that statistical relationship? Can you guess?
So the joint PDF and the joint CDF would characterize that relationship?
Yes, but there's a functional relationship between the two. If you know one, there's a one-on-one mapping. अगर आपको एक पता है, so you can guess 100% what the other one is, right? So this is a functional relationship between the two random variables, right? So if you knew one, the other one is perfectly known, right? But then there may be other random variables out there which do not have that functional relationship, yet there is a statistical relationship between the two, right?
Right, sir.
And the example that I can give you is the number of cigarettes a person smokes a day, right? And the which is x, and y is the life expectancy. Okay, both of them are random, right? Both of them are random, but knowing one, you cannot say for sure what the other one is. So right, so there's no functional relationship between the two, but there is a statistical relationship, right? I'm going to talk about these relationships when I talk about independence a little bit more.
Okay, sir. Thank you.
All right. What we're going to do next is, hold on. Okay, so what we're going to do next is talk about conditional probability mass functions or conditional density functions. Okay, just like we defined conditional probabilities, right? We're going to extend that idea to functions which are conditionally defined as well. So conditional probability density function and conditional probability mass function, right? So earlier what we did was we defined something called a conditional probability, right? Which was conditioned on not necessarily a random variable, but rather only an event, right? And that event could, for example, be we know that the random variable that is in question, there's a constraint on what values that random variable can take, or there's some other external parameter. Was it day or was it morning? Okay, and those were the conditioning we talked about. Now we're going to generalize that idea to two random variables. Okay, and conditional probability mass function. And the example I can give you is exactly the Mohsen the number of cigarettes you smoke a day and the life expectancy, right? So one of them is a random variable x, and the other one is a random variable y. And the kind of question I would ask is, given that you know that somebody smokes, let's say, 10 cigarettes a day, what is the statistical behavior of that person's life expectancy, right? Given the observation that that person smokes 10 cigarettes a day, right? So now I'm talking about two random variables. There's this random variable, which is the number of cigarettes that you smoke, right? Which is y, perhaps, right? and your life expectancy, which is X. Okay, so conditional PMFs are defined on, once again, two random variables as far as we're concerned for this chapter. And so the probability that X given Y is defined as the probability that the random variable capital X equals small x, given that the random variable capital Y has been observed to be equal to small y, right? So this is the definition of the conditional probability mass function, right? Can I write this as a function of the joint PMF? Can I write this as a function of the joint PMF? Anyone? Isha?
Sir, yes, you can, but I'm just thinking over that. How would that be?
How would that be? Why? क्या चल रहा है आपके दिमाग में?
Sir, if we conditional PDF as a conditional CDF perhaps first and then as a PMF.
Right. So this is, we're talking about probability mass functions, right? So so that means X and Y are discrete random variables, right? So this is something you know when we're talking about PMFs, right? So I should have explicitly stated this. Like, so let capital X and let capital Y be discrete random variables, right? So then this is the conditional PMF, which is a probability that capital X equals X given capital Y equals Y. Ji Mohsen?
सर इनकी intersection over conditioning event की probability के perspective से देखें तो
exactly, right? So this is just the idea that was the idea जो हम perhaps we talked about in chapter 1 or chapter 2, I guess, right? Sorry, in lecture 1 or lecture 2, right? So this is just the probability that capital X equals small x intersection with the probability that capital equals small y. So it's a joint probability of these two events divided by the probability that y equals y, right? And this therefore implies that the probability mass function, which is a conditional mass function of X given Y, is actually equal to the joint PMF divided by the marginal PMF, right? So this is a very quick derivation of how the joint PMF and the conditional PMFs are related. Okay, and you can extend these ideas to conditional PDF as well. So let me explicitly say it out here. Let X and Y be continuous random variables. Right? Let X and Y be continuous random variables. And the conditional PDF of the random variable capital X given an observation of the random variable Y is equal to, and I'm not doing a proof here, the joint PDF divided by the PDF of Y. Come on. Fy of Y, right? And this is a simple enough statement. Okay. All right. Any questions here? Right. You may very well ask, can capital Y be equal to small y? Isn't that a probability zero event? Right. So what do you mean, Keji, I've observed the random variable capital Y to be equal to small y? Even uske the probability zero hai, so how can you really observe that? Does anybody have anything to say there? Right, so that's a deeper point. I'd let you think about it, right? So how can you really observe that the random variable capital Y turns out to be equal to small y, even though that's a zero probability event? Okay? So think about that, right? So let's do an example. And the example I want to do here is actually that same circle example that we did in the last class. And I am going to write down the results directly without going over the proofs again, right? So we said kg fxy right. So we said that capital X and capital Y are random variables, and recall the robot example. We said kg a robot is uniformly distributed on a unit circle, and there is, if it's jointly uniform in a unit circle, the joint PMF or joint PDF was equal to what? क्यों जी, क्या ख्याल है? So this was equal to 1 upon pi as long as x squared plus y squared is less than equal to 1, and the PDF is 0 outside the circle, right? And from this, we marginalized, right? We marginalized over the joint PDF to determine the marginal PDFs, right? So we determined that the marginal PDF of X was equal to, what was it equal to? Root 1 minus X squared. And there was a 2 here, I forget. So 2 upon pi. Yeah. Sorry. So this is the result we had, right? And this was absolute value of X is less than 1 and 0 otherwise, right? And similarly, Fy of Y turned out to be exactly the same, which is 2 by pi, the same form, 1 minus y squared for all values of y which are between -1 and +1 and 0 otherwise. Acha. Given all of this information, what do you think the conditional PDF of X is, given that you make an observation on Y? So how do you go about this? So recall. So the random variables X and Y are jointly distributed on this unit circle, right? So where this is X, this is Y, this is +1, -1, +1, -1. Okay. The conditional PMF, conditional PDF. I mean, who would help me here? Kyun Shoaib? Okay, Mohsen, go ahead.
So joint PDF over the marginalized PDF of Y. Expression तो लिख लिया लेकिन zero नहीं handle हो रहा sir.
Right. So this is fxy xy divided by fx of sorry fy of y. Okay. And mind you, okay, so one of the things zero जो handle आपने वाली बात की ना, so यहाँ पे मैं I can put in a disclaimer here. I can put in a disclaimer here that fy of y is not equal to 0, right? So it's only defined for those values for which fy of y is not 0. Okay. And actually for those values for which this is 0, this conditional PDF turns out to be 0, right? And that makes sense actually. Similarly, the disclaimer here is going to be that the probability y of y is not equal to 0, right? So you don't have those divide by 0 problems, which may be bothering you, Mohsin. अब अगर बताएं Shoaib, you raise your hand as well.
सर ये तो इसके अलावा into u of y अगर लिख दें.
U of y, sorry. What do you mean?
Yes, so basically हमें 0 हैंडल करने ना, तो अदरवाइज वाला केस.
Yeah.
या सो हमने पहले भी पढ़ा था कि कहते हैं कंडीशनल प्रोबेबिलिटी में उसमें कि इट्स द एफ ऑफ एक्स अपॉन द प्रोबेबिलिटी इनटू द क्या कहते हैं यू ऑफ एक्स माइनस ए माइनस यू ऑफ एक्स माइनस बी. आई एम ट्राइंग टू मतलब पॉइंट टुवर्ड दैट. सो यहाँ पे सो ओके सो यहाँ पे दैट्स व्हाई आई वाज सेइंग कि यू ऑफ वाई अगर आप लिख दें.
Right, so you see, Shoaib, all you'll do is you'll just use, you look at this and you just plug in the numerator. All you need to do is you need to plug in the numerator and the denominator from the expressions that you're given above, right? And
Okay.
right, and let me state categorically here, right? So let me state this categorically if you're listening. For all values of absolute, all values of y which satisfy the absolute value of y being less than 1, right? So that's the only place where I'm going to define the function for now. Okay? So that the confusion is removed with regards to divide by 0, right? If that is true, that means if y of y sirf is jagah pe jata hai aur kahin jata hi nahi hai, right? So there's no problem whatsoever as far as dividing by 0 is concerned, right? So all you need to do is you plug in the numerator, you plug in the denominator, and if I plug in the numerator, I know that this is equal to 1 upon pi, and the denominator is for all values of y that I've initially constrained myself to be in, ye value hai 1 minus y squared, and this is x squared plus y squared is less than equal to 1 for all values of here, and blah blah ye 0 otherwise. Okay, and I can modify this slightly. Pi cancels, right? So this is 1 upon 2 root 1 minus y squared. और यहाँ पे the constraint x squared plus y squared plus is less than equal to 1. I'm just going to modify it a little bit in terms of a constraint on x. This is minus root 1 minus y squared is less than equal to x is less than equal to plus 1 minus y squared, and is 0 otherwise. Right, so this is the conditional PDF that I have for the example given above. इसका मतलब क्या है? Let's talk about that for a bit. What kind of a PDF is this? Isha, you have a question?
Yes, sir. My question is regarding the constraint. के constraint हमारा on x क्यों है and why isn't it कि हम simply उसको on y ही यहाँ पर भी treat कर रहे हो?
क्योंकि the function is defined on x, right? Right. I want to see कि I've observed that capital Y equals small y, right? I've observed that already, right?
Oh, okay, it's clear now.
Let's say I take this perspective, and that perspective is that I observe that what small y is. I've already made that observation, right? Given that observation, I'm interested in knowing how is x distributed. What kind of a distribution, what kind of a random variable would x be, given that I've made the observation that capital Y equals, let's say, 0.5. Okay? So that means I have to define some condition on x. And the reason why I do this is to make another point clear, which is what kind of a random variable would this conditional x be, right? So given some observation on x, or given some observation on y, what kind of a random variable does x appear to be here?
Okay, so sir, even when we're defining it on X, the condition that mod y is less than 1 still holds.
Yes, it still holds. But
Yes.
otherwise वहाँ पे क्या होता? वो √1 - y squared है, तो then this would have been a complex
Exactly.
number. We can't go there.
ठीक है.
ठीक है? Mohsen, you raised your hand. What kind of a random
Yes,
variable?
sir. So it looks like a uniform distribution, like, and it's dependent on y.
Right, excellent. Right? So, लेकिन if I tell you that y is fixed,
And then it's a constant across all values of x. So
exactly,
uniform.
excellent, right? So given that you've made the observation कि वो something y is, कि आपने देखा कि यार robot था, and somebody tells you कि यार the robot has a y coordinate equals to, let's say, 0.5, right? And I don't know what x is, right? Can you try to figure out for me what distribution would x follow, right? So this is in some sense Bayesian inference as well. Given y, can you make a guess about what x? ठीक है, या उसकी statistics कैसी हैं, right? And it turns out that given y, x is uniformly distributed between some range minus and symmetric around some negative value and some positive value, okay? And uniformly distributed. It's just that those values depend on what observation of y did you have, right? So in particular, if I go back to this figure here, right? Let's say आपको कोई कहता है कि यार y कुछ 0.5 है, right? So this is 0.5. So what is x equal to? X is going to be uniformly distributed anywhere between √1 minus y squared. Oh, sorry, मैंने उल्टा कर दिया. I have given y, right? Right. So given that y equals 0.5, let's say, yeah, right? X is ranges between what and what? X ranges between this value, which is what value?
Under root of 0.75.
Under root, let's make this a little general. Under √1 minus y squared. And what is this value here? This is minus under √1 minus y squared. Okay? And it's uniformly, x is uniformly distributed with these two values, right? Now you can say what happens when y increases or decreases. What happens when y is close to 1? I mean, is there the uncertainty in x, is that smaller or higher?
Smaller?
Smaller, right? So when you say okay, y is, let's say, 0.99, right? Right, so then that means x is once again uniformly distributed, but it's uniformly distributed between two values which are very, very close to 1. Oh, sorry, which are very, very close to 0. Okay, uniformly distributed between two values which are very, very close to 0, right? So the width of that uncertainty is very, very small, or the variance of x is going to be very small, given that y is close to either +1 or -1 will be exactly the same thing is going to happen. And the biggest amount of uncertainty is going to be when somebody tells you that the y coordinate is 0, right? And that means x could be anywhere between -1 and +1, right? So these types of discussions would give you an idea of what these conditional PDFs represent. Okay? All right. And one of the other things I want you to observe is that the PDF on X was not uniform. वो ये थी, right? And this condition PDF on X given Y has actually changed the behavior on X. Okay? So there's some sort of relationship or statistical relationship between, or dependency between X and Y in this particular example. And we're going to talk about this in just a bit. Okay? Perhaps towards the end of the class. Right. Any questions here before I move? Okay, so I'm going to leave this as a reading exercise, example 5.10, I believe. 5.10 is just it's a bit of calculus there, which should be good to revise, completing squares, some integrals, some Gaussian PDFs. So this, I'm leaving this off as a reading assignment. Okay. Right. Any questions? Okay. So the next section we're going to talk about is expected values involving pairs of random variables, right? So the definition I have for you is, now you have two random variables x and a random variable y. What is the expectation of the function of both two random variables? Right? So there's a function g, right, which takes as input not one variable but two variables, the variable x and the variable y, right? What do you think the expectation should be? I mean, what is it defined as? G. Mohsin.
So G function applied on the expectations of X and Y.
What do you mean expectation applied on the expectations?
So individual expectations, यानी expectation of X and expectation of Y. उनके ऊपर जो G function का relationship है वही replicate हो जाएगा in the expectation.
But what if the function is not separable? आप जो कह रहे हैं ना, that's slightly a specific case. I mean, I want some general. So let me give you, Shoaib, I'm going to come to you. Just recall this. Okay, expected value, if there was just one variable g of x, ठीक है, तो वो क्या होता था? So most of this would have been x and fx of x. I mean, for continuous random variable, discrete random variable, you just replace integral with the summation, right? Now, given this definition, Shoaib, what do you think the expectation of this two-dimensional function should be?
जी सर, सो ये होगा g of x comma y into f of x comma y और टू दो इंटीग्रल आ जाएंगे। इन सर ये जो राइट साइड पे भी जो आपने किया हुआ है उसमें भी x की बजाय g of x आना चाहिए ना?
Oh, sorry. Thank you. Right, this is g of x. Thank you. Right, so Shoaib, you're right. This is a double integral. This is the definition, right? G of x, y. And this is this is just a generalization of the concept that we've done already, right? Multiplied by the joint PDF. And of course, if this was a continuous random variable, or if this was the two were discrete random variables, you would have used summations instead of integrals. Okay, and the integral, of course, is from minus infinity to plus infinity. Okay. Now, just a quick sanity check, if you will, right? And that sanity check is, okay, right? So there's some sanity check in a box here. And that is, okay, let's say, what if g of xy was actually some function which was equal to g of x, right? So let's not use g of x. Let's say h of x, right? So h of x, if you think about it, it is a two-dimensional function, right? I mean, you can generalize it to say this is a two-dimensional function. It's just that it does not change for any values of y, but you can have that y as an input and say कि y के ऊपर असल में dependency नहीं है, right? And if I just apply the definition, this would have implied that expected value of h of x, which is equal to expected value of g of xy, and this should, by the definition, should be a double integral, and this should be h of x here, and fxy, xy, dx, dy, right? Now, here's the reason why I say this is a sanity check. Why? Because this appears to be at odds with the definition I have up above, right? You see, एक definition ये और एक definition ये. You can't have two definitions for the same thing, right? Unless they turn out to be the same. Can you prove that one, if I apply this definition one to this particular problem, this two is going to translate into that definition one? Can you prove it somehow? And just calculus. जी मोहसिन.
Sir, marginalization कर सकते हैं इसकी.
Exactly.
Across
This I
y.
know that h of x is not a function of y, so therefore I can take the integral inside. So this is h of x, okay? And this is the integral on y. And I can have an integral dx outside. Okay? And so, I mean, this is a bracket here, and this is a bracket here. And then I see कि यार ये जो चीज़ है ना, this is equal to what? क्यों ईशा? What is this equal to?
Sir, CDF.
CDF? How is the CDF? This is minus infinity to plus infinity.
Sir, because the integral of a PDF is a CDF.
Right, but it's evaluated at plus infinity. So you're right, the integral is a but we're talking about joints here. Josefa, what do you think?
Sir, this is the marginal PDF of x.
Good, right? So this is the marginal PDF on x. This is something we did last time. This is fx of x, right? And therefore, this is integral of h of x, fx of x dx, and that is nothing but the definition one per se, right? So there's nothing wrong here. Our sanity should prevail, right? Sanity prevails, right? So the definition that I gave you up above is actually nothing but a generalization of the things that we've done earlier. And these definitions per se could be applied to single random variables as well, right? So there's no inconsistency. There's nothing. I mean, you're building on top without destroying the foundations. Okay? Or rather, I would say this is the foundation on which the other things stood. I mean, that's another way you look at it, right? I look at it. Okay? Achha. Questions here? Right. So there's something called the correlation. Okay. So I think. Okay. Now, correlation. Have you heard of correlation? I mean, in what context have you heard about correlation? I mean, you should have heard about correlations. Linear algebra.
So basically, it defines the relationship between two variables, that how changing one affects the other.
Yeah. Statistically, have you heard about correlation in the statistical sense? I mean, is that something you're familiar with?
No, sir. Just that I know that broadly, like you could define it as like a positive or negative correlation. Or
Okay. Right. So, are you familiar with inner products? Advanced DSP बहुत सारे लोग ले रहे हैं, linear algebra undergraduates में ले चुके हैं. Are you familiar with inner products of vectors? You should be familiar, right? I saw somebody with a raised hand. Mohsin?
Yes, sir. Sir, मैं कहने लगा था कि signals का overlap देखने के लिए correlation function use होता है.
Right. So
और
signals
inner product
के साथ भी correlation defined है, vectors के साथ भी correlation defined है, जो कैसे में inner product होता है. So, I mean, without going into a lot of details, I mean, this linear algebra is actually much more general, and we say that there are some things called vectors, and those vectors are not necessarily vectors in Euclidean space as you would think. कि कोई चीजें होती हैं vectors abstract, और उसके ऊपर कोई abstract एक operations होते हैं जो inner product कहलाते हैं, right? It turns out that this correlation is linked to that. If you think about of random variables as vectors, and that the broad umbrella of linear algebra actually covers not only vectors or not only Euclidean vectors, but also signals, but also random variables as well. Okay? Bahral, we will not go into those details a whole lot, but if you're studying ADSP, that you can try to create links there. If you're studying LST, you can try to create links there as well. We're only going to talk about correlations as they apply to random variables in the statistical sense, without really talking about just relationships, general signals के साथ क्या है, ये vectors के साथ क्या है. Okay, so correlation is defined as, so I'm going to give you the definition of what correlation is. Correlation between two random variables, x and y, is defined as, so I am going to use this notation R to represent correlation, right? Rxy is defined as expected value of the product of x and y, right? So that's the definition of what correlation represents. Okay, and this is equal to minus infinity to plus infinity. किसके बराबर होगा? So we've done the definition up above, right? This would be g of xy. So this is actually a general, some specific case of the function g of xy, where g of xy is actually equal to x times y, right? So this is just x times y times the joint PDF. Oops. F xy times the x times the fy, right? So this is the definition of correlation, right? So, and just a pointer here with you, okay, if Rxy equals 0, we say that x, y are orthogonal, right? So this is once again a definition, if you will. Okay, if the correlation between two random variables turns out to be 0, we define those two random variables. We say that those two random variables are said to be orthogonal to each other. Okay? And by the way, Euclidean space में अगर दो vectors हैं, and I say that they're orthogonal, उसका क्या मतलब होता है?
Dot product 0.
Their dot product is 0, right? So their angle is 90 degrees, which is just another way of saying, okay, their dot product is 0, right? Which is the inner product is 0. And this definition actually comes from, or this, we say that's orthogonal, it actually comes from that fact. Okay, जब dot product 0 होता है, and correlation can be thought of as a dot product between two random variables. Okay, so this is the definition that we use, right? And one use could be is, okay, if I ask you to find expected value of x plus y whole squared, what is this going to be equal to? I can just expand the squared, and this is expected value of x squared plus y squared plus 2 times xy. And I know that expectation is a linear operator, so therefore this says expected value of x squared plus expected value of y squared plus 2 times the correlation between x and y. Right? Does it ring any bell?
Variance?
Variance, not necessarily with vectors के साथ connections. If I add two vectors up and I ask कि जी इन दोनों vectors का जो sum है उसकी length squared अगर आपने निकालनी है, right? So you have a cosine law. And Pythagoras theorem is what? X squared or hypotenuse squared equals base squared plus perpendicular squared, right? Only when, or is applicable only when it's in a right angle triangle, right? And so these are the same ideas, right? So you say KG, which is equal to, this is equal to expected value of x squared plus expected value of y squared when x, y are orthogonal, right? So this is, I mean, some analogies with Pythagoras theorem, if you will, or the law of cosine, if you will. Okay? Achha. Then there's something called covariance. Achha, just for me to get an idea, have you guys done this correlation, statistical correlation in stats classes you would have taken, or probability classes that you would have taken?
सिर्फ स्टैट्स तो हम बट मतलब कोड नहीं है, प्रोबेबिलिटी में हमने पढ़ा था, बट दैट वाज वेरी बेसिक के पॉजिटिव कोरिलेशन है, नेगेटिव कोरिलेशन है, एंड इट्स रिलेशन विद कोवेरिएंस, दैट्स इट.
Okay, so and that's only for zero mean random variables. So ठीक है, positive correlation. So this is a quantified definition of correlation. Okay, this is a quantified definition of what correlation really is. Achha, then there's something called covariance. And covariance is defined as covariance between x and y, which is often denoted by CXY and is defined as expected value of x minus the mean of x times the expected value of y minus the mean of y. Okay. And this would really then be, I would have had a double integral. This is x minus mu x times y minus mu y times fxy xy times dx dy. Right? Now, Jisha.
Sir, when we started off with correlation, we began with an intuitive definition of how we can actually see it.
Yeah.
But it's a bit hard to see covariance. And then also related to the fact that if x and y are centered at zero, I mean their mean is zero, then it would be the same as the correlation itself.
Right. So you can think of covariance as, so let's say what if mu x was 0 and mu y was 0 in the covariance? Is there a difference between correlation and covariance?
So that's exactly what I said, that then it seems to be the same.
Exactly. They seem to be the same, right? So if the one thing that we can establish, therefore, is that if you have random variables which are zero mean, both of them, their covariance is nothing but the correlation, right? Now, what about random variables which are not zero mean, right? Unki covariance, how do you define covariance? Anybody can help me here? Let's see. Okay. Can you link that with correlation somehow? And this is linked with a central moment as well. I mean, remember we talked about moments and then we talked about central moments, right? So yahan pe bhi ek centralization, if you will, if that's even a word, right? That's a theme here. So, आप Euclidean space में अगर कोई vectors लें, which are not necessarily of the origin, right? And I say, yeah, let me bring them to the origin first, and then compute the dot product between the two. Right? I could say that, right? And this is exactly similar. And I say, which is KR, random variables hai, usko let me subtract the mean first to make that random variable unbiased, right? And once I've made that unbiased, both of those random variables unbiased, and then after making them unbiased, if I compute the correlation between those unbiased random variables, that is defined as the covariance. Okay?
Sir, this brings up another question then. And that would be that if we're actually making a reference origin in a way when we're subtracting the mean,
Yeah.
then why wouldn't we subtract the mean for one of the variables from both of them? Why would we subtract the mean for x from x and for that of y from
Because
y?
you want to make both of them centered around 0. You want to make them both
Isn't
of
it
them.
that we're actually in one once we're observing it in one, you can say, space perhaps?
आप उसको space आप उसके साथ directly link ना करें. So both of them have different means. I want to bring them both of them down to 0. Okay, that's what I want to do. Right, and then after subtracting the mean, then I want to compute the correlation. Okay.
But in case of correlation, it isn't necessary that x and y were centered at 0. Is that?
Yeah.
It's a bit confusing
Yeah,
to visualize
So
covariance.
correlation is just a definition which applies to any random variable. Covariance is just a definition, but it applies to any random variables. All we're saying is that when the random variables are 0 mean, then the correlation computed for the two random variables turns out to be exactly the same as a correlation as a covariance computed for those two random variables. Okay? However, if they're not 0 mean, then the correlation computed for those two random variables is not the same as the covariance computed for those two random variables. And there is a relationship between them. Okay? What is that relationship, by the way? I can compute that relationship. उससे पहले Shoaib, I think you raised your hand. Do you have a question?
जी सर, मैं कह रहा था कि ये y माइनस म्यू एक्स व्यू y के ऊपर ट्रांसपोज नहीं आएगा?
नहीं सर, ट्रांसपोज क्यों आना चाहिए? Because they are not vectors really.
तो दैट मींस कि हम सिर्फ अच्छा
So
सिर्फ हम अभी R1 में
आप वो कंफ्यूज कर रहे हैं, वापस अलजेब्रा में चले गए आप कि जी वेक्टर्स होते हैं तो फिर एक रो वेक्टर था डॉट रख लेने के लिए.
जी.
That's not what we're doing. We have random variables which are scalar quantities.
Yes.
Yeah, they're not vectors. Right? I mean, they're not that vector. I mean, they can be thought of as an abstract vector, but not that vector that you're confusing it with. Okay? So let me just quickly give a theorem here, which basically gives you a definite relationship between the covariance and the correlation. And that is the covariance of xy is actually equal to the correlation of xy minus the product of the means. Okay. How would you prove this? Isha?
Sir, expectation की जो properties होती हैं वो apply करके it would come out to be expectation of x minus mu x into expectation of y minus mu y.
Right, so I just expand this product, right? So this is expected value. I'm going to get 4 terms. This is xy plus the product of the two means minus mu x times y minus mu y times x, right? And then I know that expectation is a linear operator that can go inside the summation. So this is rxy, right? Plus the product of the means mu x mu y. And then what? This is mu x times expected value of y and minus mu y times expected value of x.
Sir?
Yeah.
I'm not sure if that's the case with everybody, but I somehow cannot see anything.
Yes.
It's the same.
It's the same. Let's see. All right. Okay. So I go from the line up above, from here to here, right? By just applying the linearity of the expectation operation. And I've been able to pull this out, by the way, right? So this can come out of the expectation. This can come out of the expectation because it's just constant, right? And what do I get? This should be pretty straightforward from here. This is just Rxy minus mu x mu y, and that completes the proof. Right, and this basically tells me, by the way, if any one of the two variables is zero mean, the correlation and covariance is going to turn out to be the same because there's a product there. Okay. Right, and one use that I can give you for the covariance is when you're computing variances, right? So what can I say about the variance of x plus y? So how do I compute? Let's say I have a random variable which is x plus y, right? So x is a random variable, y is a random variable, and then I add them up and I get x plus y, which is another random variable, right? With, let's say, which is z. What is the variance of these two new random variables z? How do I compute that?
Product of
G Mohsin.
So expectation of x plus y whole squared minus expectation of x plus y squared.
All right, not exactly. So you see, एक छोटी सी गलती है इसके अंदर, whatever you said, right? So let's say this is z, right? So this is therefore expected value of z minus the mean of z whole squared. ठीक है Mohsin?
Right.
Right. So what is z? Z is x plus y.
X plus y.
What is mu z, which is the mean of z, x plus y? So expectation can go inside the sum. So expected value of the sum of x and y is actually equal to the sum of the means of x and y. Right? So this is minus mu x minus mu y whole squared. Right? So there's a box here, which is expected value of z is equal to expected value of x plus y, which is mu x plus mu y. And all I've done is I've just plugged this back in there. Okay? Achha, how do I expand this? The way I'm going to do this is play a little bit clever to get that relationship that I want, which is, let me pull this here and plus y minus mu y here, and then this is the whole squared, right? Because of which this is expected value of x minus mu x whole squared plus expected value of y minus mu y whole squared. And what do I have next? This is plus 2 times expected value of the product of these two terms. This is expanded by x and y minus mu y. ठीक है? So ये क्या मिला? Right, so this implies that variance of x plus z is actually equal to the variance of x plus the variance of y and plus 2 times covariance between x and y. Right, so this is an interesting result and a very useful result. Okay, now all of this leads to a definition of something which is very, very useful, and which is something called the correlation coefficient.
सर ये वेरिएंस ऑफ x प्लस y होगा ना?
जी,
वेरिएंस ऑफ x प्लस z लिखा हुआ है आपने।
sorry, thank you. This is x plus y. Okay. So correlation coefficient, have you heard of the name? Pearson correlation coefficient बड़ा इस्तेमाल होता है signals के लिए, discrete signals के लिए भी, continuous signals के लिए भी. And the idea here is similar as well, right? So it turns out the correlation coefficient between two random variables x and y is defined as the covariance of x and y divided by the standard deviation of x multiplied with standard deviation of y, so which is basically the variance of x times variance of y square root, right? So this is covariance of x, y divided by sigma x times sigma y, right? So this is the definition of something called the correlation coefficient. An important property of the correlation coefficient is the following, and I'm not going to do a proof here. The proof is there in the textbook. Which is that the correlation coefficient, the absolute value of the correlation coefficient is always less than equal to 1, always, right? And the proof, इसको मेरे ख्याल में Cauchy-Schwarz inequality से proof किया जाता है, or I mean, it's one of the ways to do it. This is through the Cauchy-Schwarz inequality, right? So the correlation coefficient is something which is always less than equal to 1, right? Now, what does it represent? So that's like something that Shoaib sort of referred to. Shoaib, आपने कहा था कि हमने पढ़ा था positive correlation होती है और negative correlation होती है, right?
Yes, sir.
Right. So वो क्या पढ़ा था? What do you mean by that?
Positive correlation means there is a strong similarity sort of between the data,
yeah,
and negative correlation implies otherwise there is the data are highly non-similar.
Okay, so typically, I mean, for sort of an intuitive level, the way this is explained is typically if you have a positive correlation between two random variables, that means increasing one in general increases the other as well, always. Okay, and that is true to an extent. I mean, when you say there's a positive correlation between two random variables, what that means is if I increase one, I would expect the other one to increase. And there's a negative correlation means increasing one would on average decrease the other, right? So therefore, if you go back to the examples of x and y being the life expectancy and the number of cigarettes that a person smokes a day, right? There will be most likely, I say most likely because I'm just talking from observations and not necessarily data that I have. Most likely, the correlation between these two random variables is going to be negative, right? Because you increase one, the other one would decrease. Okay? But then the point is, what do you mean if something with two random variables has a correlation coefficient of 0.2 versus a correlation coefficient of 0.8, right? What does that quantification signify? Right? So 0.8 versus 0.2, what does that mean? जी मौसम
सर इसको strong or weak correlation कहते होते हैं ना कि a change in x would result in a higher change in y if there's a strong correlation.
Yeah.
And vice versa.
Right. So give me a minute, please. I need to put my chart dongle on chart. So Mohsin, that's not necessarily true if you're talking about the correlation coefficient, right? And the correlation coefficient, what I want to say here, it does capture the correlation between X and Y. It sort of captures the linear dependency between the two, right? And I may have something more to say about this when we start talking about independent random variables and the difference between independence and uncorrelatedness. But all I want to say here at the moment is that when rho x y is equal to 0, what does that mean? That means that's the simplest case. I mean, when would rho x y be equal to 0? Isha, I'm going to come to this to you after this. When do you think? When do you think rho xy is going to be equal to 0? What property does x and y have to satisfy for the correlation coefficient to be 0?
Sir, one would not be depending on the other.
Not necessarily. And I'm going to give you counter examples for that later. So dependency is not related to its correlation or uncorrelatedness, strictly speaking. And there's a fundamental difference. At the same time, Mars, they are not orthogonal either. Orthogonal तब होते हैं जब जो है correlation 0 होती है. Right? So we have a covariance in the numerator and not the correlation in the numerator as far as the definition is concerned. So rho xy equals 0 if and only if x and y are not orthogonal, but something else. Mars, did I say something about this? Or did I not? Oh, okay, I did not. ठीक है. So I'll do this here. If and only if covariance, sorry, my bad. If only covariance xy equals 0. ठीक है? And in this case, x and y are said to be uncorrelated. I understand that this may be sort of confusing. I mean, now that I think about this, by the way, I mean, ये मेरे ज़हन में इतना बैठ गया कि I never thought about this before. कि when what we're saying is कि when two random variables की correlation 0 है, तब वो orthogonal है, और covariance 0 है तो वो uncorrelated है. Right? I don't know if anybody else made that connection or not. I mean, strictly speaking, you should have said कि अगर वो correlation 0 है तो uncorrelated होने चाहिए थे. But that's not how we define things. I mean, so the definitions are different. Definitions are if the correlation between two random variables is 0, they are said to be orthogonal. And if their covariance is 0, they are said to be uncorrelated. Okay? So the correlation coefficient being equal to 0 means that they are uncorrelated random variables, right? They're said to be uncorrelated random variables, right? So once again, they're said to be, right? So this is a standard definition that we adopt, right? So many years ago, people said, this is the definition we're going to follow.
Sir, can you show why?
क्या why?
From
देखिए,
कि जो हमने covariance की definition ऊपर लिखी है.
Yeah.
Can we use that to say कि अगर वो 0 हो रही है तो कैसे वो uncorrelatedness को translate करेगी?
See, this is a definition. This is people, lots of years ago, they decided कि यार, when covariance equals 0, let us define these two random variables to be uncorrelated. Let's just say मेरा नाम मोमिन है, right? Somebody gave me a name just like that. People gave that a name and which was uncorrelated random variables. And historic reasons उसके क्या है? I'm not do not know exactly. Perhaps that's another thing that you could look into and let me know. ठीक है, उसके historic reasons क्या हैं इस definition? जी शोएब.
Sir, अगर x और y independent भी हैं, then also we cannot say कि covariance 0 होगी, isn't it?
So I'm going to talk about them that in the next class.
Okay, sir.
Okay, we're going to spend some time on that, right? But before I end the class, I do want to say something else, which is when rho xy equals 1, or the absolute value of the correlation coefficient equals 1. This is if and only if, and this can be proved as well, y equals cx. That is, there is a linear deterministic relationship between the two. Ji, Isha, go ahead.
Sir, my question was regarding the fact that negative correlation can be modeled as positive correlation if we look at the complement case.
Negative correlation can be modeled as positive correlation. What do you mean by that?
For example, that you just gave the example of two
Second.
events like वो life expectancy वाला जो है.
Yeah, yeah,
So if we take that,
yeah.
so we could actually model a negative correlation as a positive correlation in that case as well. If we look at, for instance, death rates, maybe
Hmm.
that would be a complement case to life expectancy.
So you would have to define a random variable, right? When I say life expectancy, I have a very clear definition of what the random variable is. And that random variable is the age at which you die. Right? Uska
Okay.
complement kya hoga? I mean, what
The
is the
age
complement?
greater than that.
That's not really, I mean, the age at which you live, that doesn't make sense.
The age greater than that. Living through the age greater than that.
That doesn't make sense. आप अगर उसको वाकई करना चाहते हैं तो चले, which has, आप ये कर दें कि अच्छा, if the random variable y is 20 minus the number of cigarettes you smoke a day.
Oh, okay.
But then there's a negative correlation, or then there's a positive correlation,
Positive, yes.
right? But that doesn't make sense with it. I mean, there's no practical significance to that.
Okay.
Okay? Or you can say the number of hours you exercise in a day and the life expectancy. There's a positive correlation there. Okay? But the point, this last point is important, which is that when the correlation coefficient turns out to be equal to 1, the absolute value of that turns out to be equal to 1. That is possible if and only if there is a linear or an affine relationship between the two random variables. And that relationship needs to be deterministic. Okay? So that essentially gives us an idea that correlation essentially, or correlation coefficient essentially, tries to capture the linear dependency between two random variables. Okay? Sort of a linear fit between two random variables, if you will. कि उसका best estimate linear क्या होगा, ठीक है? If it turns out correlation coefficient turns out to be equal to 1, that means that they very, very much reside on a straight line, right? They're spread or they scatter, right? And it turns out that the absolute value of rho xy equals 1, so इसमें होता है when rho xy equals plus 1 is possible only when c is positive, and rho xy equals minus 1 only when c is negative, and is independent of what value c is, right? And that comes back to Mohsin's point as well. Okay, relationship slowly increasing है या fastly increasing है, correlation coefficient same रहेगा. Right? So the correlation coefficient does not capture कि एक को increase करने से दूसरा कितना ज़्यादा increase होता है. That is not what it captures. Right? What it captures is the linear relationship. The linear कितना है. Okay, so that's extremely important, right? So extremely important once again is this is independent. No matter what c is, as long as it's not equal to 0. Okay. So this is where I'm going to stop. and take any questions if you have any.